All right, it's worth talking about what happens about how we charge conductors. When conductors bearing charge are connected, they will share the charge. How the charge is divided will be complicated based on the shape of the conductors. But what's basically going on here, of course, is that if we have, say, some, let's make your book happy, we have some negative charges over here, some excess negative charge, and let's say we even have some excess positive charge over here, and then we connect them with a wire or other conducting surface, then these electrons are repelling each other. Oops. So some of them flow across the wire, and they come in here and they cancel. Oops. They cancel these guys. And then some more, right? So that might have been 2 of those. But there are still 3, and so some of those will also move around. And we would end up with, it's a little unfortunate, we'd end up with, let's say we'd start with 4. We'd end up with, say, 2 free on this one, and 2 free on this one. They would neutralize first and then divide. How they divide is pretty complicated based on the shape of the conductors, except if the conductors are spheres. We'll come back later about why and how they choose where to go, and there'll be something called equipotential surface, and that's what they try and form. But for spheres, it's very easy. The charge will be divided, and it'll divide according to the radius of the sphere. So maybe not divided by, but maybe we should say according to. As an example, if a sphere containing 6 coulombs of charge plus 6 coulombs here is connected to an uncharged identical sphere like this, then they would share that charge equally, so each would get 3 coulombs of charge. On the other hand, if we start with the same 6 coulomb thing and we put it on a twice as large sphere, so plus 6 and that, this would yield not 3 and 3, but 2 and 4, because the twice as large radius would get twice as much charge. All right, the Earth is, in effect, a really big conducting sphere. Close enough, at least. So when a conductor is connected to the Earth, we say it's been grounded, usually by literally sticking a wire into the ground. But the Earth is huge compared to any real-world object you're going to put on it, so when charge is quote-unquote shared, basically all of it ends up on the Earth, and the conductor ends up discharged. The Earth is also essentially neutral, too, and no charge you add will materially change that. Your 3 or 4 coulombs is as nothing when divided over the entire surface of the Earth, and so it looks like the charge just vanishes. Charge doesn't go away, it's conserved, but we're not able to account for it because it becomes so vastly diffused. So, hooking something up to the ground, a grounding wire, basically cancels out the charge on it. If it has excess negatives, they flow into the Earth. If it has a deficit of negatives, then electrons will flow out of the Earth into it and cancel it. In both cases, the conductor ends up discharged, and the Earth essentially remains discharged. Now consider bringing a negatively charged rod near but not touching a grounded conductor. The rod repels the electrons in the conductor. So if we look at something like this, we have this rod, and we have this sphere or whatever, and we're going to ground it, and the symbol for grounding is something like this, a long and a short wire. So we're going to bring in a negatively charged rod. So over here, of course, we have some number of negative charges, but they're matched, of course, by positive charges because the conductor started off neutral. When we bring in these charges, they repel some of these charges. So we should get rid of maybe 1, 2, 3 of them, because they flow to the ground where they are lost. Now, if we cut the grounding wire, so that we can no longer pull charge from or towards the Earth. And then we remove, so then we have an excess charge. And if we then remove this rod, we still have excess positive charge on the conductor because we've driven off some of the negatives and we've left their positive nuclei behind, and now they can't get back because of the break in the ground wire. This is what's called charging by induction. We have induced, we have induced charge, I don't know what happened, but on our sphere, without adding it directly, looks like we created it, we've really drawn it from the Earth. All right, metal spheres 1 and 2 are touching. Both are initial neutral. And then we have the charge rod is brought near but does not touch number 1. It's removed, and then the spheres are separated. What can we say about the charges on the sphere? Well, there wasn't anywhere to get charge, anywhere for charge to go. So although at first we would end up getting negative charges would have been repelled. So at first, these positive charges, would have attracted negative charges near them, which would leave positive charges over here. And so it looks like we've induced some charge, but once we get rid of the charging rod, then these electrons are free to move again, and they would like to be over here with that guy, and so they go neutral again. So we end up with no charge on either. All right, same setup. Metal spheres 1 and 2 are initially touching. Both are initially neutral. Then we bring a charge rod near. The spheres are then separated, and the charge rod is removed. Afterward, what kind of charges do we have? Here we're going to have negative on sphere 1 and positive on sphere 2. You might cry foul and say, how could that be? But it goes back to what we had just said about the charges. When we bring the charge in, and here's the rod, then we attract some negatives, which leaves behind some positives. And remember, we have some positives here as well. We then separate the spheres, but we have, remember, kept the rod there. So there's still these positives, which means the negatives were still attracted over, and the positives were still over here. And then we pull away, we remove the rod, and we can see that we have negatives over here and positives over here. This again is a case of charging by induction. We haven't really created charge, but we forced their separation, and now they're on isolated objects that we could treat as positive or negative objects. Identical metal spheres are initially charged as shown. P and Q are touched together and separated, then Q and R are touched together and separated. Afterward, the charge on sphere R is whatever. And so first we bring together P and Q. They're identical, so they're going to add charge together. Their net charge is 2. These two together have 2 coulombs, and they're going to split them equally. So 2 nanocoulombs. And they're going to split them evenly. And then, so now we have 1, 1, and -1 nanocoulombs. Then we bring Q and R together, but they have 0 total charge. So all the charge cancels out, has been neutralized, and we're left with one charge here, but no charge on either of these. So our answer would be C.